let me give you a warning. I will not give you this warning anymore in the year, okay? That generally in a group, when it's the kind of group where you have to provide input, okay, and you have to get involved, usually the easy things come at the beginning of like the session or whatever, okay? And questions get progressively harder because they rely on previous stuff, right? So, you know, usually people say like, oh, can someone brainstorm things for, you know, whatever topic? The first one is obviously the easiest because no one has said anything yet. So you can put in whatever simple basic thing and it's like, yes, that's great because no one else has said anything, okay? Now, today's lesson is no different, okay? So I'm going to give you that warning. If you don't want to get in while it's easy, fine. But I'll pick someone later on and you might regret it. Last chance. Anyone want to volunteer what their sentence was? Yes, Helen.
The gradient of the exponential function increases at an increasing rate towards positive.
Okay, all right.
And that's all I got.
That's good. That's a good start. Okay, let's go with this. Okay, the gradient increases at an increasing rate. Okay, which sure enough it does. Okay, what would it do if it was only increasing but at a constant rate? What would it look like?
Straight line.
No. That constant gradient.
Ah, what's going on? Hold on. Be careful with your language here. This is why I asked you to write it. Okay. The gradient is increasing at an increasing rate. That's what this is doing. If the gradient is increasing at a constant rate, okay, the gradient might be 1 at a particular moment. The next moment it might be 2. If it was increasing at a constant rate, what would it be at the next moment? It would be 3, and then 4, and then 5. Does that look like a straight line to you? No. That's not a straight line. Now I'll let you have a think about this. By the way, so, we'll get to the limit question that I asked you yet. That actually, it was Ruben who asked it, didn't it? Yeah. Oh, ridiculous. Okay. Fine. He gets no answer from me. Okay. We will address that question, but you're going to notice me doing this a lot. Okay. I'm going to give you questions, and I'm just going to let them sit in your brains because that's where they will give the most benefit. If I give you the answer, it's kind of like, you know, it's like reading spoilers. You're like, oh, okay, that's how it ends, but it ruins the experience, you know. So I'm going to do that a lot. You actually know, all of you know what the function looks like if the gradient is increasing at a constant rate. You definitely know enough calculus to work it out on your own. What kind of function is it? You can be very specific. We'll get to that later on. Now that's as x approaches positive infinity. What's it doing on the left-hand side? What's it doing on the left-hand side? Okay, the gradient is now, at this point we have to be very careful. We're thinking about the left-hand side. We're saying the gradient is decreasing. Stop. What does that mean? What does that mean? We're going from this way to the left. A lower gradient means it's shallower, isn't it? Okay, and that's true enough. That's what kind of shape you get. Right? It's not getting steeper. It's not like a cubic and falling off the other end. Okay, so the gradient is decreasing. Now, what do we say here? Okay, you have to be careful because some of you will say, I actually heard both answers. Some will say at an increasing rate, but some of you will say at a decreasing rate. Which one is it? Now, I'm not going to answer that question at the moment. Part of the reason why is because it's just a semantic difficulty, okay? If you wanted to, you could kind of justify either answer depending on what you meant by increasing or decreasing, okay? You always want to try and make your communication in all fields, not just maths, as unambiguous as possible. So, can we say it in a more specific way? The gradient is decreasing, but it's doing it in a way that, you know, let's see. Let's have a think about this guy. Again, I'm going to ask the question, what's happening as you go from this way to negative infinity? Okay? What's happening to the gradient?
Decreasing at a decreasing rate.
What's the gradient, I'm just thinking about the gradient, at this exact point?
0.
0. What might the gradient be here?
Negative.
How does it look? Maybe like it's not quite 45 degrees, is it? Maybe it's like minus 2/3 or something like that. Okay, if I go a little further, you know, that looks like the tangent might be 45, so maybe that's minus 1. Okay, and maybe minus 3, or you get the idea. As I go this way, I am decreasing, aren't I? The gradient is decreasing, okay, because it's getting more and more negative. But this kind of behavior is totally different to this kind of behavior. So can we come up with a better way to say it? Okay, a more accurate, less ambiguous way. Okay. Now, I'll spare you it. I won't always give you annoying questions that I don't answer. Okay, I think probably the easiest way to say it is, as x approaches negative infinity, okay, I'm using this limit language very deliberately, right? The gradient, actually we have notation for that, dy and dx, right? It's approaching something as well. Unlike this. See this? This is not approaching anything. It's going to keep on going more and more negative forever. Okay, no limits. But here, this does go toward a limit, namely 0. Okay, I suppose if we wanted to tie it all up together in one sentence, one mathematical sentence, we could say the limit as x approaches negative infinity of dy on dx, that limit is 0. Okay, those two things are the same. Okay, good. Now, what does the gradient function actually look like? Now, I went around and I saw lots of different things, but basically, your gradient function looked a lot like your original function, which is correct. Okay, it is. Now, I'm going to draw in my best shot at the gradient function. Don't forget this is 2 to the x. Okay, I want you to compare mine to yours. What ways is it similar? What ways is it different? Okay, here's what I've got. That's off, but it'll have to do. Yeah. So, this graph underneath, okay, that's dy on dx. Okay. Now you'll notice a few things. Number one, my gradient function is below the original function. Okay. Who drew theirs like that? Anyone? Maybe I should ask. Who actually got to drawing one? Hands up. What did I see? I must have seen your 3dx. Ah, come on, 4-year class, you knew better than that. Okay. It's below, right? I wonder where you might have drawn it. Some of you might have drawn it above. It would still behave according to the rules that you just set, right? You also notice it's not like 3 to the x. This is missing a crucial feature that 3 to the x had, okay? Do you know 3 to the x and 2 to the x, they shared this intercept. You remember that? Why was that? Because anything to the power of 0 is always going to be 1, okay? But this is not. I very deliberately put it underneath, okay? Why? We can get to that shortly. Okay. The last thing is it's underneath. It stays underneath forever, and it's approaching underneath in a way that is mirroring the kind of rate at which 2 to the x is. 3 to the x didn't do that. Do you remember? 3 to the x sort of hugged the asymptote a lot more tightly. Okay, because we said it grows faster, it also shrinks faster. Okay, because it's all at the base. 3, 5, 100. The bigger that number is, the more extreme its behavior is.